I'm going to start on this fourth box right here where it talks about if you have two chords that intersect in a circle. It says the products of the measures of the segments of these chords are equal. So I'm going to try to simplify this to be part times part of one chord is equal to part times part of the other chord. Sorry for the bad handwriting. Yep, that says part times part, and then equals part times part of the other chord. So that's like my dumbed down way of like explaining this rule. Let me show you guys some examples where this applies. So this only applies when we see two chords intersecting. So let's go to the next page where we can see some examples. Okay, so if we look at number four has two chords intersecting in it. Hopefully we observe the tick marks, and so that segment has to be 6 inches also. So I'm going to apply this part times part equals part times part rule to this problem. I'll show you guys what we get. Okay, so the two parts that make up one chord are 6 and 6. So we would do 6 times 6 equals, for the other chord, 1.5 times x. Again, sorry for the bad handwriting on my screen. Okay, so on the left side, we get 36. And on the right side of the equals, we get just 1.5x. Divide both sides by 1.5, and we get 24. And then we have units on this problem, so it's 24 inches. Okay, another problem where we see two chords intersecting. Let's see. Okay, so number 5 is another case where we have two chords intersecting. So we can see OD, segment OD is a diameter, but still a chord. So this rule still applies even with diameters. So same thing, I'm going to apply the part times part equals part times part rule. Okay, so we got 24 times 24 from one of the chords equals, so on this one we have 12 for one of the segments of the chord, and the rest of that chord we don't know what it is. We'll just call it x for an unknown. Okay, that's an x. So we get 12 times x for that side of the equals. So 24 times 24, 576. Okay, so yeah, we get 576 equals 12x, divide 576 by 12, we get 48 feet. So that's x. So that means the diameter has to be 48 plus 12. So we know the diameter has to be 60. So the radius would be half of that, which is 30. Let me write that out. Okay, so there we go. So radius is 30 on number 5. I'm going to point out the other two problems where you would use the part times part case. That would be number 7 and number 12. Those are the only other two examples where we have two chords intersecting. So you'll see the notes all filled out in Google Classroom. I'm just going to point out that you would use those rules. So look at the algebra I do on those problems. Try to work them yourself and see if you get the same answers, but all of the step by step on those problems on Google Classroom. Okay, let's talk about a different rule. Okay, so we talked about this rule where part times part case for two chords. I want to talk about where two tangent segments meet at the same exterior point outside the circle. That's what this box talks about. So if two segments from a common exterior point are tangent to a circle, they are congruent. I call this the tan equals tan case. So it's got the geometric notation for how you'd write it on this one, where AC equals AB. So we could even put the tick marks here. Since those are two tangent segments meeting the same exterior point. I'm going to show you guys on number 1 how this one could help us problem solve something like where this rule would apply. So this, on number 1, it says, let me grab the screen. Okay, so triangle TRW is circumscribed about a circle A. So we see the circle such that it's touching all the sides of a triangle. All those sides of the triangle are tangent to the circle. And for instance, WT and WR meet at the same exterior point of W. So this rule applies right here, where tangent equals tangent. Okay, let me draw on the screen tick marks where this would be relevant. So we see WK would have to be congruent to WM based on this rule, and then TK would have to be congruent to TL, and LR would have to be congruent to MR, since those two tangent segments meet at the same exterior point of R, just like this picture right here. I'm going to label the given information. So TK is 3, so that means TL would also have to be 3. WM is 9.5, so that means WK would also have to be 9.5. And there's a couple ways to solve this problem based on the perimeter of this triangle being 50. But I'll just solve it algebraically. So these are our two unknown sides currently. And once I find like LR, that would help me find TR. So let me write the algebra to this. I'm going to call these two unknown sides just X. Okay, so this is the equation. So you would just add up all the segment pieces for this triangle, set equal to perimeter, and then go about solving it. So I have this on Google Classroom all filled out. But you combine all like terms, solve this eventually, and you get X is 12.5. You'll see all the steps on Google Classroom. And then if X is 12.5, that means TR would have to be part plus part, 3 plus 12.5. So TR is ultimately 15.5. Okay, this next rule underneath the tan case is if we have a radius and a tangent, they are always perpendicular at the point of tangency. So on your notes, I would say draw the radius such that it touches that point of tangency. So I'm going to do the best of my ability on the screen. That's okay. And the radius and the tangent line will always be perpendicular. So let me show you guys where this is helpful. Okay, so on number 3, we see there's a radius of 12 and then 16 is a tangent segment. So anytime we see those two lines meet each other, a radius and a tangent, we can say there's a right angle at that point of tangency. So we see this triangle is a right triangle, so we're going to apply what we know, Pythagorean theorem, to help us find this missing side. We'll call it C since it's the hypotenuse of this right triangle. And that will help us find X. So let's do that. So we'll solve Pythagorean theorem for this. 12 squared plus 16 squared equals C squared. So I'll write it out. Okay, so after doing Pythagorean theorem, we find the hypotenuse of that right triangle to be 20. Notice the radius is 12, and so all the radii on our circle are congruent. So this piece right here is also got to be 12. Therefore, X has to be 20 minus 12, which we know is 8. So anytime you'll see a radius and a tangent, you'll see this show up a lot on the murder mystery activity. You're going to want to put a right angle at that point of tangency, and that'll allow you to do things like Pythagorean theorem on this kind of problem. So this one's important for today's activity. Okay, these are the last two rules I want to talk about. So this rule right here on the front side of the notes describes if you have two secant lines that intersect at the same outside point on a circle. So this rule only applies if you see two secant segments. So this piece right here, this explains best what those words are trying to say. So if you take the whole segment of one of the secants and multiply it to its outside segment, so in this case, AD would be the outside segment, and then set it equal to the whole length of the other secant, and then multiply it by its outside piece, that those should be equal to each other. So this describes best this kind of situation. So let me point out on the other side of the notes where we would see two secant lines, and this rule would help us. Okay, so number 8 is an example where this rule will apply. We see two secant lines that connect to the same outside point of the circle. So I'm going to apply that whole times outside piece. So first of all, we have to figure out the whole length of this secant line would be part plus part, so x plus 6. The outside segment that we identify is 6. So x plus 6 is the whole length out times 6 equals the whole length of the other secant, which is 18 plus 8, which is 26. And then the outside segment for that secant is 8. So we do 26 times 8 on the other side equals. And then we can just solve it. Okay, so skipped ahead. So just showing the steps of how you would solve it and then ultimately get 28.6 repeating. So let me point out the other example where you'd use the secant case. So on 11, this is also where you'd use the whole times outside equals whole times outside. So let me just set y'all up on this. So the whole length of this secant would be 4 plus 8, which is 12. The outside segment's 4, so you do 12 times 4 for one side of the equation. And then on the other segment, you would have x plus 2 for the whole length of that secant. And then the outside piece is x. So you'd have x plus 2 all in parentheses times x, if it'll let me write it. Okay, so this one right here, this is a set of, my handwriting's better on Google Classroom filled out notes. This one ends up being a quadratic because you end up getting an x squared term right here. So you end up having to factor it like what we've talked about a lot of time before. So just go to Google Classroom for the filled out version for this example, okay? Let me talk about the last rule. Okay, last rule talks about if you have a tangent segment and a secant segment that meet at the same exterior point. Like in this diagram, they all meet at A, so secant's AB, and then the tangent's AC. So this rule is the whole times the outside piece for the secant line will be equal to the tangent measure squared. So just like on that last rule, you want to identify the whole length of the secant, multiply it to the outside segment of the secant, and then set it equal to the tangent measure squared. So let me show you guys an example where that would happen. Okay, so number 9, TR is a tangent and then SR is a secant. So this is where this rule would apply. So the tangent measure is 12, the whole secant segment 16, and then the outside piece for this secant's x. Okay, so the whole length of the secant is 16, the outside piece is x, and then equal to the tangent measured squared. So it'd be 12 squared. So just following the formula that I just pointed out. So this is 16x equals 144. And then 144 divided by 16 would ultimately be 9. Same thing on 10. We see a tangent and a secant. So this rule will apply also. So the whole length of the secant is x plus 5. And fix this. So we're going to do x plus 5 for the whole length of the secant times the outside segment, which is x, and then equals the tangent measure squared, 6 squared. Okay, so we'd have to distribute the x, so you end up getting x squared plus 5x equals 36. So this is a quadratic equation, so we have to set this equal to 0 to solve. Minus 36 from both sides. Okay, so we're looking for factors of negative 36 that add up to 5 to factor this. So those magical numbers are 9 and 4, where the 4 is negative. So it's plus 9 minus 4. So let me write this out. Okay, so these are the factors, x plus 9, x minus 4. So the solutions would be negative 9 and positive 4. And so based on the picture, the only one we accept as an answer is x equals 4. And that's it.